So good afternoon. I thought I'm going to make a video today about corrosion and contacts in general and why this is such a problem for low voltage signals, say like anything what is not a switched signal, where you turn on a headlight with 50 watts and you got several amps flying or floating through it. And we're talking here, for instance, on the 126s and 124s of the TD signal and the 5-volt signals, which are distributed from the ECU for the temperature and for the speed. I believe that's the two 5-volt signals, 0 to 5 volts, analog signals which come out. The TD signal is generated, as we know, by the EZL, and it should have a range somewhere at a minimum of 8 volts up to 12, 14 volts, whatever the battery is supplying at the time, whether the engine is running, which it is running at that point anyway. And this way, we know if we have good signals or bad signals. And most of the time, the electronic devices we have, including a lot of the sensors, are not really bad, and they're difficult to troubleshoot. And I'm pretty sure that many viewers have tried to swap out control boxes and sensors and actuators to find out that it really doesn't make any difference. Before, I would suggest to try by swapping these expensive units out, is to examine thoroughly the entire wiring in the vehicle to be worked on. And this problem is even more so prevalent beginning with the 202 and the 140 and the R129, where CAN bus was introduced, and I will get to that at the end of the video. This video is going to have basically the beginning part, or we're going to deal with connectors, how they corrode, the 4 different versions or forms of corrosion you will encounter, and what this actually looks like it and how it affects the metals, and what remedies there are, if there are any. And then the second part, the shorter part, is going to be an introduction to CAN bus for those people who are not familiar with CAN and the issues. We want to discuss this here first so you can actually see what these things look like. And while that is so important to take care of these issues, to have a properly running car, because this can cause a lot of problems, and these type of corrosion issues can create a intermittent problem. This means you have it at some time and then other times you don't until the connection gets so bad that the unit completely stops working, or whatever is in that circuit. So I got an example here of a typically corroded connector. This is a picture I found on the internet for a Ford. I forgot which one it was. And this is a thing, what I dislike about the newer cars, say like anywhere from the 90s on, they went to smaller and smaller connectors for signals. And of course, as smaller a connector is less surface you have, and that means there is less connectivity between the plug and the receptacle. Either way, between the two contacts, the male and the female contact part. And the first version of, let me just show you a typical composition of a contact. That could be now male or female. This is a gold nickel copper plating assembly. So one is built on top of the other. And of course, the plating processes, they're not 100%. You will get a plating surface, especially in the thicknesses we're talking about, which is usually less than 1/64th or 1/100th of an inch, which is like 0.1 millimeter and below. It could be only a tenth of a millimeter, you know, or hundredths of a millimeter in thickness if you're going with that. So these platings are very, very thin. And as we know, this has been substituted. So you could have, for instance, instead of gold, you could have silver or a chrome finish, a chrome plating finish, silver finish, or you can have, what was the other one they use a lot as, now I forgot it. Well, that's usually the three big ones, is gold, silver, or chrome, or a form of chrome, because there's a greater variety of chrome plating out there of what you can actually add to it. And of course the other one, now I forgot the fourth one, nickel cadmium. That could be also a cadmium plating, cadmium nickel copper. The cadmium platings is usually used on the low cost connectors. Those are the cheapest ones you can buy. The better ones then are the chrome plated ones. Then comes the silver ones, and then on top of it is the gold plated ones. Now the Mercedes-Benz ones here, those are silver plated. Let me just see if I can show you this. This is a brand new male connector for Mercedes-Benz, as they were used with the solder eyelet. Here, I don't know if it's gonna let me zoom in or not. Probably not because of the background. Let me see this here. Yeah, now you can actually see it. I have to bring this in so it actually focuses on it. So here you can see this. This is the typical Mercedes-Benz male plug. And these are my preferred ones because you have a very large surface of contact area. And then we have the new one. This is the female of it, also with an eyelet. You can either go straight through or you can come from the back. They're soldered in. 6337 is the solder you use on those. Come back here. And those mate. And they have a very large mating surfaces. See this? So you have from here to here. So this is the mating surface from where my thumbnail is here all the way in. And this is about, I would say, 1/4 of an inch, 3/8 of an inch. This is the typical connection. And what happens with this is, you can see, this is pore corrosion. That means that the plating wasn't fully sealed. And you have moisture or other additives going through. That is a very common corrosion issue. And what that looks like, would be a connector which is affected by it. You can see this, they have this dull finish, black matte. Again, this is the new one here, just so that you see this in comparison. This is, and I got this one here out of my car. So let me see if I can enhance this by using our light. Yeah, and you can see this on the inside as well. Even though it looks clean, it is corroded. And in my other video, I had shown to use one of these wire brushes here, these here, and you can see this, they will fit in here, and you can just rotate this in, and they will go all the way in eventually. I do this with the electric drill. You can see you can get all the way in. The only problem with this is you're basically destroying the outer plating. But you can see this, we have basically now a polished inside. So this looks pretty clean, but the surface is now rough. Let me see if I can zoom in better. I gotta go right in front of the camera. I figured finally out where the camera actually is. Yeah. So here you can see this. And you have this mirror finish with streaks in it. That comes from the brush. But this basically has removed the pore corrosion which was in there. And again, you can see the pore corrosion it gives us that dull finish. This is basically what pore corrosion looks like. Let me see, there we go. Sorry. This is what that looks like at pore corrosion. You can see the shiny surface now on the inside. So this is the only remedy we have. And this is a connector here. Let me just show you this. This connector here has just regular. This is basically in the beginning. And I had cleaned those out. That's why they have the shiny surface in there. You can see that mirror kind of finish with streaks. So there comes a point, and this is basically what pore corrosion looks like it on the male plug, which was fully inserted into the, let me see if we can zoom in here. This won't let me zoom. There we go. You can see the dull finish on top and the scratches. This is pore corrosion. This is what you got mostly on the Mercedes-Benz on these type of connectors, is pore corrosion. Now let me go back out and let me show you what this actually does. It creates these cracks, and you can see here's the copper nickel, and they open up and they get these cracks and crevices, and the nickel and the copper and the chrome, or the silver in this case, breaks down and it disappears, and that lets moisture enter, and that moisture then will start the corrosion process. That is the common way on how this actually happens in those. And this here is the next form of corrosion. This is corrosion when you have electrolysis. This happens with the connectors, which carry larger currents, where the pore corrosion has started, and then you apply a high current, say like 2 amps to 10 amps, 20 amps, in that range, 2 at 12 volts. That's what they will do. They will break this then down, and they will really start to rust because you're forming electrolysis. And as long as that happens, that's usually your headlight lamps. That is the two clutches for the AC air compressor, for the AC compressor, and for the air pump. They have clutches. Any type of light, the horns, they draw quite a current. Reversing lights, all of your lights, the turn signals, everything that is switched with a higher than 2 amp current, which is a lot of stuff, they will start to look like this. And this is again electrolysis, corrosion from electrolysis. Then the next one is fretting, and that is connectors which are exposed to vibration. That is all the connectors you have, even at low currents, which are mounted on the engine and then to the harness, because the harness eventually will exit somewhere, the engine, and the harness vibrates because the sensor or switch or the actuators, the EHA valve, the idle speed control valve, or what have you, any type of switch basically, or actuator. It could be also on a fuel injected system with electronic fuel injection, intermittent or pulsing systems, that they're also exposed to this. And you can see here is that one part moves and the other part is stationary, and that's starting to basically scratch up the plated surfaces, and then eventually it will work its way all the way down to the bare copper and into the copper, and that will then start to rust, especially when the car sits, and that would be then electrolysis, corrosion by electrolysis, and pore corrosion. You will have both of these corrosions. There is a paste, electrical paste or grease, what people put in there. They will reduce this, but eventually it will happen. And the lower part would be basically your switch, your actuator, your injection valve, fuel injector. And the top part is basically the mating connector part to it. So it could be male, female, or reversed. But this is basically what that looks like. And I had another picture here which showed us this here in the 2 steps. So it starts out here with a little bit, then it goes and it moves further and further out with the vibration. And then it eventually digs itself a hole into the other material. And then you're gonna have very poor connectivity. This type of corrosion cannot be detected. Any of these 3-4 forms of corrosion what I've shown cannot be detected by continuity tests. And I have a continuity tester here. I wanted to show you. Let me see if I can zoom out. Of course, now it doesn't let me do it. Let me zoom out. For whatever reason, it doesn't. This is one of these here. You have seen them probably. They have this here and this here. And then they have an LED in with a 12-volt battery, actually. I guess that's what that is. And with those ones, they will always indicate continuity. The only way you can measure this is by actually measuring currents. And this higher of a current you put through there is better. You can measure this, but for that you need special test equipment, which most people don't have. The only option you have left to inspect this for corrosion, unless it is as visible as he had it in the first picture, is by physically examining the parts. This here again with the blackish, and then this here, you can see this here on how that actually looks like it. See? It loses the focus. Or if you have actually a unit here like this here, this is the fuel pump relay, you can see that they have become a gold color. A golden color, and they're black on the inside. And they actually look like this here too when they're new. So here you can see the difference between the two. And the same goes, these are the actual sockets. These units will fit in. They have the center hole here, the pin, and they go in like this here, so you can see this. And if you were to rebuild them, you would have to get a lot of these here and desolder the wires from your harness and then insert them in here. And then they basically go in like this, and then they fold over and lock it in place. And then you can actually insert the unit. And this is very difficult. These are difficult to clean off. And then there comes the question is to buy a new one. Now this is the aftermarket fuel pump relay I have. And you can see this is somewhat better, but this has already issues too. And that unit is not that old, as you can see. And you can see this, that they have also. This is basically what the beginning of the plating looks like. Not the plating, the corrosion. The poor corrosion looks like it. That's poor corrosion in the beginning. And those are cadmium plated. You can see this, they're fairly new. And even though they're somewhat similar in color, the cadmium has a slightly duller appearance when they're new than silver. And this is the reason why these parts from Mercedes-Benz are fairly expensive. They're like $2.50 for one of these connectors, male or female. And I bought 100 of them each because I'm redoing the entire harness. And I wish Mercedes-Benz would sell them in bulk, see, like in a pack of 50 or 100, and reduce the price down, you know. But the silver and gold plated ones, especially these ones, are expensive. So this gives you an idea. Now, the reason why this is so critical is, let me show you now, we're going into the segment about the TD signal, which is critical. Then again, the temperature sensor, the which one is this? The 11 B10-2, I believe it is, from the engine. That is a resistive unit. Just see that we get the right one. Yeah. And basically what we're looking at is a TTL signal from, no, let me start there with the analog signal first, from the B10-2, I believe it is, that is the temperature sensor for the coolant temperature and ambient temperature. And that signal is picked up as a resistive signal measurement by the ECU and then processed and converted through an op-amp into a analog output signal from 0 to 5 volts, depending on the resistive measurement they did. And this signal goes to the idle speed control unit for determination on the RPM it should have and how long it will take until it, drops down to 650 after starting. And that signal goes over to, that analog signal goes over to the fuel pump relay. That's where the fuel pump relay determines whether or not to activate the cold start valve, if it has minus 10 degrees Celsius or 15 degrees F. The second resistive temperature sensor in that unit goes over to the EZL. So that gets a resistive measurement. It does its own resistive measurement. They were separated, so it's like a control mechanism. But they both don't communicate. Now the EZL in turn puts out this type of signal. And this is a 50% duty cycle signal and is called the TD signal. That is your RPM, and that will change in frequency, which means as higher the RPM is more narrower, shorter in duration. The on-off cycle is on-off, or recessive and dominant, And they don't really have a TTL signal. They go with the signal at a bare minimum from 8 volts all the way up to 14 volts. So if you measure this signal and with an oscilloscope, you will see it is going to hover around somewhere 8 to 12 volts. On the new units I have on the EZL, it is right around 11.5 volts with 14.1 volts coming from the alternator when the battery is fully charged. Over time, the signal deteriorates, and then it goes down, and under 8 volts, it is no longer, cannot be processed by all the units which receive that RPM signal. That's the tacho, the RPM gauge, basically. That is the idle speed control unit, the ECU, and the fuel pump relay. And I believe there's one more device which gets us, I think, the AC compressor relay as well. That's besides the speed signal, which is coming from the speedometer, which is also an 8 to 12 volt on-off square wave, basically frequency controlled. And you can see this on how difficult this already is with these relatively large signals from 8 to 12 volts or 8 to 14 volts for the on position. Anytime this is below 8 volts, the other units will no longer recognize this as a recessive part of the signal you're sending over, or the on signal. So that's why that is critical, that it doesn't drop below 8 volts. Now the CAN bus itself, by its structure, let me just go and jump over here. I found those, is usually this here. So you have the actual computer or control unit, you have whatever it is for your seat belts, for the ASR, for the engine. On the V12s, you have 2 of them for the ignition system, and the throttle plates, they're connected through this. They have a controller, which is nowadays usually integrated into the microcontroller. Back when this started, when I first worked with this, the CAN controller was a separate chip, and the CAN transceiver was a separate chip. The CAN transceiver today is still a separate chip, and it is based on the RS-485 protocol. And what they mean by NOT A to NOT X, these are all the control modules sitting on the CAN bus. And you can see the CAN bus has a termination on each end of it. And for that, on the newer cars, anything past W202, 140 and R129, if you work on any of these cars and newer, the first thing you need to check is by removing one of the control modules and figure out your CAN high and CAN low contact point, and then use a resistive, an ohm meter, and see if you got 60 ohms. You have two 120 ohm resistors in parallel. That means you should be measuring 60 ohm. If you don't measure 60 ohm, if you measure 120 or infinite, or anything which is higher than 120 basically, then that means you have a substantial wiring issue, and you have to figure out where the two terminating resistors on that in that wiring harness are located. And then you have to troubleshoot this through with continuity testing from each module to module to module, and then see where you wind up where these two resistors are. They can fail, the wiring harness can break open, and this is a common problem. Is usually one of the resistors fails or breaks, and then the CAN bus becomes erratic, and a lot of times wrong information is then sent or read wrong over the network. And that can get you these issues where it says there's a sensor bad, and you check the sensor and you check the sensor, and the sensor is okay. You put now a new sensor in, you replace that, you replace another sensor, and then the thing comes back and you can't find it, and it doesn't go away. It always comes back on. This is the first thing on CAN bus, is you have to check the signal integrity of the wiring harness, if this signal can even be sent. And the reason why this is such a circus is the voltage between dominant and recessive is only 2 volts. And what they did is now the output signal here is limited to 5 volts. So this is a 0 to 5 volt system. And with these small connectors in this corrosive environment, the signal can deteriorate very quickly, especially with the high speeds they are communicating. The latest standard now goes at a bare minimum of 250 kilobits per second. Originally and they can go up to 1 million bits per second, or 1 megabits, bits, not bytes, bits per second. As higher the signal goes, or as faster that signal is transmitted, is more critical the interconnectivity and the quality of your wiring harness becomes, because otherwise the signal gets so deteriorated that you have wrong error codes. It is a self-correcting network, and it should tell you there's a CAN bus failure. But before the unit actually recognizes a CAN bus failure, it will distort the transmission. So instead of reading a good signal, or they're telling one unit tells one unit one thing, and the other unit interprets it the wrong way, as a result out of it, is quite common. And this is what makes these cars so difficult to repair on the electronic side, is that you basically have to crawl through your entire engine harness and make sure that the CAN bus wiring especially is in absolute pristine condition, from the wiring itself to the connectors on both the module you're plugging into this and the receptacle where that plugs in. There can't be nothing there. And again, they have the signal basically floating at 2.5 volts. So there's a constant 2.5 volt voltage present on the CAN bus, and on both, on the high side and on the low side. And when they are transmitting dominant and recessive, then one goes low and the other one goes high, and you have basically a 2 volt separate difference. High minus low, that difference has to be 2 volts. And you can see this for a valid dominant signal, you need between 1.5 at the utmost low side to a maximum of 2.5. So you have only a 1 volt range here, and you have only a 1 volt range here for the recessive side. And that's basically what makes that so complicated, is these super small voltage differences in the system. And the currents are very, very small, which are transmitted. We're probably talking a bus load of maybe 1 milliamp to 10 milliamps in a 140 with a V12 engine, and I don't know how many control modules connected to it. So that is the thing, is to determine the signal quality, what you really need is a network analyzer. And there's a company, Handtech, that's a Chinese company, and they have come out with pretty decent test equipment, I have to say, which is in the $100 to $400 range. And they offer a handheld oscilloscope, digital oscilloscope, which has a CAN bus decoder, which means you can only see the waveforms on there, but it can store this and it can actually interpret the message for signal integrity. And that's how you can thoroughly examine the actual CAN bus transmissions. Because these units here, I bought one, which is an Autel. Let me just turn it on. Now you get to see me here for a second. This is an Autel. Let me see if we can go down a little bit. Yeah. Let me unlock it. There we go. And I did some diagnostics on a Lexus 2007 with this here. You can see this, they work pretty well. And I got the whole thing ran through of what was wrong or not. The only problem we have on that car, these units cannot properly diagnose the CAN bus itself. And this was a 2005 Chevy truck I was working on, for a friend of mine who got this. I got this one here, is the Maxi Pro MP808, and those are pretty good. So Autel and Handtech, Hantek, are very, very good Chinese made. These are domestic Chinese companies. They're not American or European companies. And those systems, they work pretty well. I used to have a diagnostic tool from Snap-on, and I paid a fortune back in the 2000s, in the early 2000s for it. And I still have the 40-pin connector for the W140s for that. And that was that rectangular red unit with the 4-line LC display in it. And that thumb wheel, you could go up or down, and then you could push it to enter. But again, these units here cannot tell you if this signal is actually what you're getting, and if this is within the spec. This here is the SAE J36 whatever standard. This is for CAN CAN version 2.0B now. That is the high-speed one. This is the same voltage for the CAN, the original CAN version 1.0, which came out in 1989. I think it was introduced to 88, somewhere around there. Except that the CAN 1 would go only up to 250 kilobits per second, and the CAN 2B can go up now to 1 megabits per second. In terms of frequencies, that's a good question. I don't know. We're looking probably at frequencies below 100 kilohertz, but even that is pretty high for compared to DC or the signals we're looking at with the TD signal, which is I think 400 hertz or 100 hertz per 1000, no, 400 hertz for 1000 RPM. So that will go 400 hertz up to 624 kilohertz at the very most. This one here is at least 10 times higher than that. So you may go up to 250 kilobits. But you could go up to 250 kilohertz or even 500 kilohertz or higher. And for that, you have to have extremely good connection for that to work properly. Otherwise, you will get random error messages and you will have the engine light coming on, with erroneous readings or wrong, error messages, which really don't exist. You're going to be chasing your tail. And again, these units here cannot test it. They will be able to communicate, and most likely when you hook them up, the engine is not running at first, which means there is no electrical noise, no interference, no electromagnetic interference, say like from distributor in switching electronic, ignition systems and stuff like this, which can pollute the 12 volt or 14 volt DC bus in the first place and then offset this. I just wanted to show you this. This is basically just an introduction in general of what you're up against. And I don't know if I'm going to do a sequel to this where we go further into this. I probably could use the Chevy truck we have here and hook the Handtech oscilloscope I have with network analyzer to it and show you what the CAN bus actually looks like it on a running vehicle when you monitor this. And then we could determine that. But I will have to see on how my schedule and the time looks like it. I hope that this video, I know that these videos are very long, but this is an introductory video for people and viewers who have not, gotten into this or maybe thinking about getting into this, or if they want to get a basic understanding on how this actually works. The most important thing with CAN, for anyone who has CAN bus in their car, and it really doesn't matter if that's a Mercedes-Benz, that is any one of these vehicles which have CAN buses, you have to check that the 120 ohms that you actually have a 60 ohm measurement, resistive measurement. You want to do this with the battery disconnected, so there is no power in the entire car. Everything is powered down. The CAN transceiver can accept a outside voltage on the CAN bus, like from a multimeter. They're ESD proofed, and so you cannot destroy the control units which are on that bus. But you will get a reading, and you need to measure 60 ohm. If you don't measure 60 ohm, if it is anything, I would say less than, with a 1% deviation. So 1%, that would be 59 ohms at the low side to 61 ohms at the high side. If that is outside these two, from 59 to 61 ohms, then you need to crawl through your entire wiring harness and check everything. And that has to be fixed first. And only once the CAN bus has been verified that the termination resistances are correct, then you can start relying, and your connection points are good, that they're not corroded, that they have to be absolutely in pristine condition. Then you can rule out the CAN bus itself as an error for erroneous error messages or sensor failures or problems it may indicate or may store in the main module, which you may read out. And only after that is you clear out the codes, once you have that restored, and then you have to drive the car. The error messages you're going to get after that, they're going to be valid. And then you have to check first the wiring again, because if you had wiring issues in the CAN bus, that means you're going to have wiring issues from the individual control modules to their sensors and actuators. So you have to then look at that part of the wiring first to see if this is caused by corrosion in the wiring system, in the connectors, and then you can actually go on and make a determination whether or not a sensor or actuator actually has failed, or if a control module has failed. That could be possible too, but then there's usually several things which don't work anymore. When a control module goes bad, several sensors or actuators cannot be set or read from or written to, one way or the other. And so that's kind of on how it's not magic. It's just plain forward and straight, common sense and logic. This is just all logic here. And again, is the whole point, the starting point with CAN bus, or with the TD signal, or with the signal temperature and speed from the ECU out to the other units. That's the same issue. That signal you want as good as possible, and then you have a reliable electric system in your engine, which lives off these signals basically, is going to run a lot better. Every other problem, once that's fixed, is of mechanical nature and will point, say, like with a rough running ignition, not ignition, but the rough running engine is pointing towards valves to 99% of the time. Worn out valves, cracked valves, bad seats or carbon deposits like there's no tomorrow, that kind of stuff. And then you have to think about what you want to do with your heads. But that is after all of that stuff has been checked. Then you can actually rule this out. Please feel free to comment or ask questions. I will see on how I can answer them. We may make an extra video if the question is interesting enough. Please like the video if you like it, and please subscribe if you haven't subscribed yet. This way I can get you updated on the latest what we got going here. And as a notice, is the last time, this video is now 43 minutes long, probably by the time I'm done. It took YouTube a whopping 24 hours or 26 hours actually to process my last video. That was with the uploading, the way they do this between the app and their web server, and then the actual processing by YouTube itself once it is uploaded. It took forever. So I have no clue. This is Saturday afternoon, January 21st, I believe is today. As I'm making this video, no, the 22nd, I'm sorry, Saturday the 22nd in the afternoon here in Kansas City, and either it might be alive here tonight, or it is going to come on Sunday. If you're seeing this on Sunday as a newly posted video, then you know it took YouTube hours, almost days to process this. With that, I say thank you to all my viewers and have a great weekend. And we will see you the next time when we do another video. Thank you.